Chapter 6 Thermodynamics Part A The Heat Energy. In the thermodynamics, we will study several parts. The first part we want to study is the heat energy. If we have two bodies, one its temperature is T1 greater than the other body whose temperature is T2, and then we put the two bodies in contact and isolate them from the surroundings, heat energy will flow from the hot body to the cold body till reaching the thermal equilibrium, and then they have the same final temperature. This flow of heat energy, it was found that the amount of heat energy is proportional to the mass of the body, and difference in temperature between the initial and the final temperature. So Q is the heat energy equals constant m delta T. This constant is called the specific heat, and it depends on the kind of matter we are dealing with. To sum this up, the heat energy could be calculated using mc delta T. To identify each term of this equation, we have Q is the symbol of the heat energy. Any energy is measured in joules, but the heat energy, if calculated in calorie, you can convert from calorie to joule using this equation. 1 calorie equals 4.18 joules. This is called the joule equivalent, which is the ratio between joule and calorie, which is 4.18. Q equals M. M is the mass of the body in kilograms. C is the specific heat of the matter. Its unit is joule per kilogram degree, and delta T is the temperature difference. We can use the temperature difference in Celsius or in Kelvin, as we will prove it later. Delta T is the difference in temperature. Always use it T final minus T initial. Remember that the temperature in Kelvin equals the temperature in Celsius plus 273. Let's say some notes and some remarks about this equation. In the equation, we have difference in temperature. We will prove that difference in temperature could be used using difference in Kelvin or in Celsius. If you try to find delta T in Kelvin, you will put T final in Kelvin, T initial in Kelvin, and subtract them together. Instead of T final in Kelvin, you put T final Celsius plus 273, and T initial is T initial Celsius plus 273. Subtract this together, the factor 273 will disappear. Now you will have T final Celsius minus T initial Celsius, which is delta T in Celsius. So if you have in the equation difference in temperature, you can use Kelvin or Celsius. But if you have only temperature, you use the absolute temperature. The absolute temperature is the temperature in Kelvin. You take the temperature in Celsius and add 273. Remark number 3, the temperature is a measure of the molecular activity of the system. If we draw the volume on the y-axis and the temperature on the x-axis, we found that as the temperature increases, the volume of the matter increases at constant pressure. If we extrapolate this line, we'll find it cutting the x-axis at negative 273.3, which is called the absolute zero temperature. This is the absolute temperature in Kelvin. Again, if we are calculating the difference in temperature, it's the final minus the initial. We have two probabilities. Either the T final is bigger than the T initial, which means increase in the temperature. So delta T will be a positive number. Positive number means that Q will be also positive because Q equals MC delta T. The mass is always positive. The C, the specific heat constant, is always positive. So if the sign of delta T is positive, the Q is positive, which means that this heat energy is gained by the body. So if the body gains heat energy, it will increase in temperature. And vice versa. If we have decrease in temperature, delta T in the equation will be negative. So Q, which is the heat energy, will also be negative, which means that heat energy is lost. In case of heat energy lost, the Q is negative. Remark number 6, the specific heat of the matter. We mentioned that Q equals mc delta T, so C equals Q divided by m delta T. From here, we can find its unit. Its unit is joule per kilogram per degree or per Kelvin. Its definition is it is the amount of heat energy absorbed by 1 kilogram of the matter to raise its temperature by 1 degree. This specific heat is a physical property of the matter. We have specific heat for every kind of material we are dealing with. Also, the specific heat depends on the phase of the matter, whether you are having the matter in solid phase, liquid phase, or a gas phase. Later on, we will explain that C depends on the thermal process that undergoes in the problem. The next remark, what if we will have number of moles instead of number of kilograms? Remember that number of moles equals the mass divided by the molecular weight. The equation states that Q equals mc delta T. Divide by m capital and multiply by m capital. M small over m capital by definition is the number of moles. M capital multiply C small, we will note it by C capital, which is the molar specific heat. The molar specific heat. This is another form of the law using number of moles instead of number of kilograms or mass. But now, if you are having number of moles, you don't multiply by the specific heat, you multiply by the molar specific heat. Its unit is joule per mole degree or joule per mole Kelvin. Now we have two forms of the equation, mc delta T or n capital C capital delta T. mc equals nc, which is called the heat capacity, and its unit is joule per degree. Another remark that the equation Q equals mc delta T is only valid in the same phase. When the matter is changing phase from solid to liquid or liquid to gas, we use another equation called the latent heat. Q equals mL, the latent heat, L. For example, if the matter is changing from solid to liquid, this process is called melting. Like when changing ice to water, ice is melting to water. The amount of heat is MLM. LM is the latent heat of melting. It's the amount of heat energy required to change 1 kilogram of the matter from solid to liquid. If we are changing from liquid to vapor, this process is called vaporization, and now the amount of heat could be calculated as M, latent heat of vaporization. Latent heat of vaporization is the amount of heat required to change 1 kilogram of the matter from liquid to vapor. If you want the amount of heat, multiply by the mass. So now we have three phases of matter: solid, liquid, and vapor. When you change from solid to liquid for 1 kilogram, you will need Lm, latent heat of melting. And if you change from liquid to vapor, you will need latent heat of vaporization. And the opposite process, you remove heat from the matter. You remove heat from the vapor to have it liquid, and you remove liquid to have it solid. That's why you subtract or you put negative sign for the latent heat of condensation. Let's explain this using the relation between the temperature and the Q. Let's make an experiment. This experiment, we will get a piece of ice, put it in a container, and heat the ice. So you will give the ice heat energy, and you will measure its temperature using this thermometer. Then draw T versus Q, the temperature versus the amount of heat energy given. The first step, you will have ice. Its temperature is below 0 degree. You will find the temperature of the ice increasing till reaching 0 degree. After this, you will find the temperature is constant at 0 degree. This is the temperature of melting, and you will find the ice transforming into water, but at constant temperature, melting temperature 0 degree. This experiment is done on water as an example at atmospheric pressure. After the ice completely melts into water, you will have water at 0 degree, then 10 degrees, 20 degrees, till reaching 100 degrees. 100 degrees is the boiling temperature of water. At this temperature, the temperature is constant, and now phase is changing from water to steam. Water is changing to steam. After all water is changing to steam, you will have steam at 100 degrees, then increasing to 110, 120, and so on. So we have three phases of the matter: ice, water, and steam. When changing from ice to water, the temperature is constant, and we are using the latent heat as we explained before, MLM. When you are changing from water to steam, you are using the latent heat of vaporization, water to steam, MLV. While when you are using ice and you are giving heat, the amount of heat is calculated as mc delta T, mc delta T, mc delta T. But the specific heat for ice is different from water, is different from steam. We said that the specific heat depends on the kind of matter and also depend on the phase of the matter. So water has specific heat for ice in the solid state, specific heat for water in the liquid state, specific heat for water in the vapor state, which is steam. So these are three for the three phases. If you are in the phase of the solid ice, use sea ice. mc ice delta T. If you are in the phase of the liquid, it is water, mc water delta T. And if it is in the vapor, in the vapor state or phase, use m steam delta T. This is the relation between the temperature and the heat energy given to the matter for water as an example at the atmospheric pressure. We can generalize this relation for any kind of matter and write it as follows. First of all, now we have solid, liquid, and vapor. This is not ice and this is not steam. In general, it is solid, liquid, and vapor. When you are changing from solid to liquid, use M multiply the latent heat of melting Lm. And if you are changing from liquid to vapor, use MLV, which is the latent heat of vaporization. This point is called the melting temperature. We don't know for this matter what its melting temperature, but for water it's known at 0. So according to the type of matter you have, you will find its melting temperature. And this is the boiling temperature at which the temperature here we convert from liquid to vapor. During the phase of solid, the amount of heat energy is calculated as m C solid delta T. And in the phase of the liquid, MCl delta T. And in the phase of the vapor, MCV delta T. Notice that this is the direction of increasing the heat energy, which means gaining heat energy. What will happen if we are losing heat energy? We will be in the opposite direction, this direction. In the opposite direction, we said that losing heat means that the amount of heat calculated will be negative. Now, if I'm changing the matter from vapor to liquid, this amount of heat is called latent heat of condensation. Vapor, when changing to liquid, this process is called condensation. Latent heat of condensation is negative, but the amount of latent heat of condensation is the same as latent heat of vaporization. So we can say that latent heat of condensation as an absolute value equals the latent heat of vaporization. That's why in the problems you may use latent heat of vaporization when you are changing from vapor to liquid. Similarly, when you are changing from liquid to solid, this process is called solidification or fusion. So we have latent heat of fusion, amount of heat losing to convert from liquid to solid. Latent heat of fusion is negative, but it is the same amount as the latent heat of melting. So latent heat of fusion as an absolute value equals latent heat of melting. Same amount. This process is called vaporization. The opposite is called condensation. This process is called melting. The opposite is called fusion or solidification. This was the general graph of the relation between T and Q. Now we will examine what will happen in the problem of heat exchange. This is very important to solve the problems heat exchange or heat transfer or calorimetry problem. Remember in the beginning of the lecture, we were saying we have a hot body at T1 and a cold body at temperature T2. These two bodies were put in contact within a calorimeter. Calorimeter is a thermally isolated system which prevents changing the temperature with the surrounding. What will happen that the heat energy will flow from the hot body to the cold body until thermal equilibrium is reached and they have the same final temperature. If we will apply the conservation of energy law, this means that sigma heat energies equals zero with signs. Q gained plus Q lost equals zero. If the hot body will lose 10 joules, the cold body is gaining this 10 joules. So Q gained is 10 joules plus Q lost minus 10 joules equals 0. If you will use this form of equation, put delta T equals T final minus T initial as stated before. But we can write it in another form. The amount of heat energy gained by the hot body the amount of heat energy gained by the cold body will be the same amount lost by the hot body. So here we don't want to put a sign for heat energy lost. So when you are substituting with the temperature in difference, take the big number of the temperature minus the small number to have delta T positive, as we will see in solving the problems. When thermal equilibrium is reached, we have the same T final for all the bodies. From here, we can explain the Zero's law of thermodynamics. The Zero's law of thermodynamics states that if we have two objects in thermal equilibrium with a third one, for example, A is in equilibrium with C, and B is in equilibrium with C, therefore they will also be in equilibrium with each other. A and B will be in equilibrium with each other. Now we want to solve some examples on heat energy problems. We have two kinds of problems, either heat exchange, hot body and cold body and exchanging heat, or converting from one kind of energy to the other. Let's begin with example number one. Example number one, we have a solar home contains 2000 kilograms of concrete and it is given the specific heat of concrete. It is required to calculate the amount of heat energy the concrete will lose when cooling down from 25 to 20 degrees. Simply to calculate the heat energy, it is mc delta T. The amount of concrete is 2000 kilograms. C is 1 kilojoule per kilogram degree. So the answer will be in kilojoule. Difference in temperature is the final temperature minus the initial temperature. The final is 20, the initial is 25. So Q will be negative, which means that it will be lost. And we know that when cooling down, heat energy is lost. Another example, we have heat exchange between a hot body and a cold body. The example states that 200 grams piece of lead is heated to 90 degrees. We have a piece of lead heated to 90 degrees. Its mass is 200 grams. We dropped it in a calorimeter containing water at 20 degrees and the amount of water is 500 grams. Now we want to find the final temperature of the system. You have lead at 90 and water at 20. To find the T final, it will be between 90 and 20. So the lead will lose heat energy, and the water will gain heat energy till they have the same T final. According to the equation, Q lost by the hot body, which is lead, equals Q gained by the cold body, which is water. It is given in this problem the specific heat of water and the specific heat of lead. In your sheet, you will find a lot of problems and you will go to the table to find the specific heat of the required materials. Okay, MC delta T is Q lost by lead and MC delta T is Q lost by water. Mass of lead, instead of grams, you put it in kilograms. C of lead, it will be kilojoule per kilogram. Kilojoule per kilogram is okay if it is kilojoule in the left-hand side of the equation and kilojoule in the right-hand side of the equation. Delta T. Delta T, we said in this form of equation, you use the big number minus the small number. The big number for lead 90 is bigger than T final. So put it 90 minus T final. As for water, we are sure that the T final will be greater than 20. So the big number is TF and the smaller is 20. So put T final minus 20 because we don't want sign for difference in temperature. After substituting in this equation, you will find T final equals 20.84. Another example, we have a piece of metal. This piece of metal is heated till 100 degrees. Its mass is 30 grams. It is unknown metal. We don't know this metal. And we want to calculate its specific heat using this equation. We heated this metal to 100 degrees, then we put it in water at 20 degrees, and this water was in an aluminum container. This aluminum container is 20 grams and it's made of aluminum. In this example, data is given about the container. The other example, he didn't mention anything about the kind of the container or the mass of the container. So we neglected the container. But now we will put into consideration the container. Again, we have hot body, which is the metal, and cold body. The cold body now, it's not the water only, it's the water in the container because water was put in a container so they have the same temperature. Applying the heat exchange equation, Q lost by the hot body, which is the metal, equals Q gained by the cold body, which is the water and container. Again, we will calculate the amount of heat given to the container because it is mentioned here the kind of the container and the mass of the container. But the other one, he didn't mention this. Substituting with Q lost of the metal, MC delta T of the metal, and Q gained by the water is MC delta T of water and container. For the metal, M metal, C metal is the unknown. This is the unknown I want to calculate. Delta T of the metal. Now we have metal at 100 degrees. Water and container is another body at 20 degrees. They will meet at final temperature, which is between 100 and 20. This is the final temperature. So for the container, the bigger number is 100 and T final is less than 100. So put 100 minus 25, which is the T final. T final here is given 25 degrees. As for the water, its temperature will increase from 20 to 25. So take it 25 minus 20. This is positive and this will be also positive. After substituting, you can find the specific heat of the metal. And this is an experiment we use in the lab to calculate the specific heat of unknown metal. Another example, we have a container containing ice, 150 grams of ice at 0 degree. We added steam at 100 degrees, 20 grams of steam, and it's given these data. The question is, what is the final temperature of the mixture? We want to calculate T final of the mixture. And is there any ice left in the container? In this kind of problems, we have different phases. This is ice, the solid phase of water, and this is steam, the vapor phase of water. In this problem, you must draw the relation between T and Q. T and Q. We have ice at 0 degree. This is the 0 degree. And we have steam at 100 degrees. This is steam at 100 degrees. What is the T final? We have three possibilities of the T final. The first possibility that we will have delta T, or sorry, T final is 0. This is the first possibility. Or T final is from 0 to 100, or T final is 100. I will assume either of these possibilities, and examine if it is correct or not. My advice is to start with the range of T final. I will start with this possibility. Assume that the T final is between 0 and 100, which means that steam will lose energy till reaching this T final, and ice will gain energy till reaching the same T final. For steam to reach this T final, it will make two steps. First, it will be converted into water at 100 degrees. Then it will be converted into water at less than 100 degrees. To write this, we write M steam, L condensation. But instead of L condensation, we can use L vaporization as explained before. Then another step, which is MC delta T. M steam, C water, delta T. Now the steam after condensation is water. So you use the properties of water. M steam, C water, delta T. Delta T is this difference. This difference is 100 minus T final. 100 minus T final. As for ice will melt into water using M ice, L melting. Then its temperature will increase till reaching T final using M ice, C water. After melting, the ice takes the properties of water. Delta T, difference in temperature from this point to this point, is T final minus 0, the bigger minus the small. After substituting, you will find T final equals 5 degrees. If T final equals 5 degrees, this means that steam is water and ice is water, and all we have is water. So no ice left in the container. This possibility was correct because the final answer is 5. It's between 0 and 100. Let's take another example which we will not have a correct answer. This example with another givens, it is given that we have a container containing 500 grams of water at 20 degrees, and we dropped a piece of ice at 0 degrees. Its mass is 200 grams. Given your data and asking the same question, what is the final temperature of the mixture, and is there any ice left? Again, here we have water and ice, two phases, so we have to draw T versus Q. Ice is at 0 degree. This is ice at 0 degree. Water is at 20 degrees. They will meet in between T final. Either T final is 0, this point, or T final is from 0 to 20. So now we have only two possibilities. T final equals 0, this is the first possibility, or T final is from 0 to 20. Again, we will start with the range of T final. Assume that T final is 0 to 20. What will happen if the T final is from 0 to 20? Water will lose energy till reaching T final. Ice will gain energy till reaching T final, but on two steps. Q lost by water equals Q gained by ice. M water, C water, delta T 20 is greater than T final. So 20 minus T final. As for ice, M ice Lm first to be converted to water at 0. Then M ice C water delta T. Now the ice have the properties of water, but with the same mass. So M ice C water delta T. T final is greater than 0, so it is T final minus 0. If you substitute with the givens in the problem, you will have T final negative 8.5, which is out of the assumed range. We assumed that T final equals range from 0 to 20. Now we are out of range. So this solution is wrong and this is refused. What is the other possibility? The other possibility that the final temperature is 0. So this is the answer. T final is 0. What is the meaning of the final temperature to be 0? It means that when we put the ice in the water, not all the ice melted, but part of ice melts till reaching thermal equilibrium, as if you are putting 4 pieces of ice in a glass of water. After thermal equilibrium, only one piece melts and the 3 pieces are still here. So maybe after thermal equilibrium, we don't have enough heat energy to melt all the ice. So we will rewrite the equation as if part of ice melts. So the amount of heat given by the water will be equal to the amount of melting part of the ice. Q lost by water equals Q gained by part of ice. Water will lose M water, C water, delta T. Now delta T, water will lose all its energy from 20 degrees till reaching temperature 0 degrees. 20 minus 0. On the other side of the equation, part of ice will be converted to water and melts. So m dash of ice, Lm. M dash after substituting will be 0.125 kilograms, which is 125 grams. We are starting with 200 grams of ice. So this answer is acceptable. The amount of ice that melts is less than the total amount of ice. But what we want to calculate is the amount of ice left, not the amount of ice melt. So the amount of ice we still have is 200 minus 125 grams, which is 75 grams. Another example is changing from a kind of energy to another. In this example, we have a lead bullet. This lead bullet is moving with kinetic energy. When reaching a target, it will stop. What will happen to this kinetic energy? This kinetic energy will be dissipated in friction inside the target and will be converted into heat energy. So the amount of kinetic energy lost by the bullet will be converted to heat energy, increasing the temperature of the bullet. This bullet is designed to start melting when reaching the target. If it will start melting when reaching the target, what is the minimum velocity the bullet will have to start melting when it is inside the target? If we examine the relation between T and Q, this bullet is initially at 37 degrees. It will reach till the melting temperature, which is given as 327. So it will have heat energy to just reach melting. But it will not start melting, just reach melting. So assuming all the kinetic energy of the bullet goes to heat energy of the bullet, so half mv squared equals mc delta T. M is cancelled from both sides, C is given, and delta T is the melting temperature minus the initial temperature. You will have the velocity calculated easily. Another example, also a lead bullet, but initially at 30 degrees, and it is required to completely melt. I want it to melt completely when it stops in the target. Now it will increase from 30 degrees to 327 degrees, which is the melting temperature. Then it will melt from solid to liquid using MLM. So the kinetic energy will be used to do two steps. First, to increase the temperature of the bullet from 30 to 327 mc delta T. Then will melt all the bullet. Another example, a bullet moving with speed 200 meter per second stopped in a block of wood. What is its final temperature if I have the velocity and want to find its final temperature? So the kinetic energy will be converted to heat energy, half mv squared equals mc delta T. T final is unknown. Substitute to calculate the T final. But this is not enough. I have to ask myself, is this T final is less than the melting temperature? Yes, it is less than the melting temperature. So this is correct answer. The other example is different. It is the same, But when after calculating the T final, we found it that it is bigger than the melting temperature. Let's see the other example. 30 grams lead bullet initially at 20 comes to rest in a target. So again, we have kinetic energy will be converted into heat energy. But here in this problem, assuming half the initial kinetic energy of the bullet is converted into thermal energy. So here it is stated that only half of the kinetic energy will be converted into heat energy. So half the kinetic energy will be converted into heat energy. In the previous examples, he didn't state any ratio between the kinetic and the heat. So I assumed that all the kinetic is converted into heat. If the speed of the bullet was 420 meters per second, what is the temperature after it comes to rest? And it is given all the data you want about the lead bullet. Again, I will think that half the kinetic energy will goes to heat energy, and I will put half and put the kinetic energy half mv squared equals mc delta t. And I will say that T final is unknown and the initial is 20 and calculate T final. But now T final is greater than the melting temperature. So this is a wrong way of thinking. The previous one, I did the same, but the T final reaches 176, which is still less than the melting temperature. So I was okay. But now, when I did the same, the melting temperature is smaller than this. So this is wrong. This means that the energy given to the bullet to increase its temperature, part of it is used to increase its temperature till reaching the melting temperature, and then part will melt part of the bullet. How can I solve this problem? First of all, I will calculate the amount of energy given to the bullet, which is half kinetic energy. Half the kinetic energy will give you 1323 joules. I will ask myself, this amount of energy is enough to do what? To reach T melting, or to reach T melting and completely melts, or less? So I will calculate Q1 and Q2. Q1 is the amount of heat the bullet needed to reach the melting temperature 327. It's mc delta T. I will calculate it according to the givens. It will be 1179. Then I will calculate Q2. Q2 is the amount of heat energy which the bullet can take and completely melts, which is M, total mass of the bullet, multiply Lm. Total mass of the bullet multiply Lm will give you 735. If I added Q1 and Q2, it will be 914. Is this amount sufficient to do both steps? No, it is less than both steps. It is greater than Q1, but it's less than Q1 plus Q2. So this amount of heat energy will increase the temperature of the bullet till reaching the melting temperature. And then it will melt part of the bullet, not all the bullet. So I can write the equation as half the kinetic energy will be used in mc delta T plus m dash Lm. mc delta T, m dash Lm is part of the bullet will melt. After substituting, M dash is 5.88 grams, which is less than 30 grams, the amount or the mass of the bullet. So this assumption is correct. Another example of converting energy to heat energy is the car brakes. You have car, a 400 kilograms car traveling at 80 kilometers per hour. We don't use kilometer per hour. We will need to convert it into meter per second. Is brought to rest by using its brakes. The specific heat of steel is kaza. Specific heat of steel is C steel. Steel is the material of the brakes. It is required to calculate the total mass of the steel to be contained in the brakes drums if the temperature of the brake is not to rise more than 120 degrees. Assuming that the kinetic energy of the car will all be changed to heat energy in the brakes. So half m v squared of the car will be mc delta t of the brakes, and the brakes material is steel. It's given that delta t will not exceed the 120 degrees. Substitute half mass of the car is 1500 kilograms. The velocity of the car is 80 kilometer per hour. I will convert it to meter per second, then squared equals m steel. This is the unknown. C steel is given in calorie per gram degree. I cannot use the calorie because the kinetic energy is calculated in joule. So the heat energy, the other side must be calculated in joule. So M steam and then C, you will convert from calorie to joule, multiplying by 4.18. Per gram, you will convert it into per kilogram. After substituting, you will find that the mass of the steel will be 6.3 kilograms. The last example we want to discuss is an example of three bodies. We have 0.25 kilograms of water at 20 degrees. It is mixed with 4 kilograms of aluminum at 26 degrees and zero point 0.1 kilograms of copper at 100 degrees. It is required to find the final temperature. Now we have three bodies: water at 20 degrees, aluminum at 26 degrees, and copper at 100 degrees. I want to find the final temperature. The final temperature may be between 100 and 26 and maybe between 26 and 20. I don't know. So I have two possibilities to check. Instead of this, we can use, it's easier to use this law, the other form. I will add all the Q's and put the delta T is the final temperature minus the initial temperature. Let's make it together. Q water plus Q aluminium plus Q copper equals 0. Q water, you will use the delta T, T final minus T initial. You will use the T initial of water, which is 20, and T final, whether it is bigger or smaller, I don't care. I will put it always T final minus T initial, because here I'm using heat energy with its sign, So M water, C water, T final minus T initial of the water. Again, I will make this for aluminium, M aluminium, C aluminium, T final minus T initial of the aluminium. The aluminium initially was at 26. And for copper, M copper, C copper, T final minus 100 because the copper initially was at 100. This equation has only one unknown, which is the T final. Calculate the T final to be 25.27 degrees. Of course, you will need the specific heat of the three materials you are dealing with. You will have C water, C aluminum, C copper. Thank you for listening.